Okay, so we've done our homework in terms of the probabilistic framework, right? Play around what the conditional expectation is, how can I represent this as the form of a linear line plus epsilon. Now we have everything in our mind, right? We have this picture in our mind, and we know where everything is, and I've entirely described to you what the distribution of y is. Well, just some properties on the noise that I will need, but pretty much that's it. All I'm saying here is that the conditional expectation of y given x is equal to little x is on the line a star plus b star x. That's all I'm doing here, okay? So now I want to estimate, okay? So I don't have this a star and b star. I want to estimate them from data. Okay, so what we're going to assume is that we have some random pairs, xi, yi. So now they have to really be, so those are all those dots on the scatter plot. I have a bunch of those dots. They have the same distribution as this xy I've been spending quite some time describing. And so what I assume, so saying that they have the same distribution means that they're also of the form yi is equal to a star plus b star what? xi plus epsilon I, okay? They're all close to the line up to this epsilon random variable noise, which will be of mean 0 and covariance 0 with x, okay? And we want to estimate x star, a star, and b star. So this is what we're facing as a problem, okay? Sorry, so this is a star and b star. So this is what we're facing. We have those points. They're not exactly on the line, right? So many points, and statisticians still manage to miss all of them. So they're not on any line, but we know that they're of the form being on a line plus some noise. And what we're going to do is we're going to assume that the noise is not completely overwhelming, right? Clearly, if the standard deviation of sigma is 25 times the slope of the curve, I'm never going to be able to know whether this curve is pointing upwards or downwards, okay? Because the points are going to be so far, so spread out, that I'm not going to be able to sense any deviation. But here we can see that there's clearly an upward trend. Okay, and so we're going to try to estimate from those points. So we start from here as statisticians, we're right here, and we're trying to go back to what the truth is. So this is what the truth is. Y is equal to a star plus b star x. Okay, so that's what I use to generate this data. And now this is the estimator that I propose from the points. Okay, so we'll see a technique that allows us to draw this red line, which is the one that you estimate from the data. And if any of you has seen any linear regression, this is something that you're used to, and that's the one you're used to, not the blue one. The blue one is the probabilistic setup. This is the data analytic one that says, give me data, I'll just draw a line for you. Okay? And so you can see they're not exactly equal to each other, but they're fairly close, and we're going to try to address how close they are. Okay, we're going to try to say, as the number of points on the scatter plot goes to infinity, those two lines should coincide. And one way to say this is that A hat is going to A star, and B hat is going to B star. Okay, if we understand what the fluctuations of B hat are around B star, we're even going to be able to do some tests about B star. Right, so if A hat, I'm guaranteed to be of, I don't know, close to 1.96 over square root of n away from B star, then I'm going to be able to use that to perform a test whether B star is equal to 0 or not. If I want to test, for example, if investing money even makes a difference on the Facebook campaigns, for example. So this is the estimator, okay? Statistical hammer. I had an expectation. Remember, A star and B star, we're minimizing this thing. Okay, so I take my hammer and I replace the expectation by an average. All right, now, here you can see it's actually not even an average, it's just a sum, because of course the argmin doesn't care whether I multiply this sum by 1 over n or not. It's always going to be the same argmin, but this is the same hammer. And so this I thought I corrected this. Okay. Sorry, so this is not the least squared error. This is the least squares estimator. I don't want to talk about the LSC estimator. I want to talk about the LFC. Okay? So it's the least squares estimator of AB, and it's just the minimizer of the sum of the squared errors, or the average of the squared errors. Okay, and so that gives you some B hat and A hat and B hat that looks like this. Should we spend 5 minutes or 10 minutes proving this? Of course not, because everywhere on this line where you see an expectation, you replace it by an average. And all we used was the linearity of expectation, and so it also works for the average. So every time you see E of something, just replace it by a bar on top. And that's exactly the same thing, and you can see that this is what? This is expectation of xy minus expectation of x, expectation of y. That's the empirical covariance between x and y. And this is the average of the x squared minus the square of the average, which is the sample variance. Okay, so you have the sample covariance over the sample variance. And then for A star, we had expectation of y minus B star expectation of x. And now it's just average of the y's minus B hat average of x. So this is something that's just exactly written here. I just have to take my expectations and replace them by a bar. Okay, so just do it maybe as practice so you don't have to actually just follow exactly the same thing. Is that clear for everyone?